retired physicist. I went into physics because I like physics. I still like physics. We've been talking in this group on a couple of different occasions about quantum computing and quantum cryptography. I thought it might be useful to go over some of the background to those topics. And so I proposed to John Rudy that I would give 3 talks on quantum mechanics, on the basics of quantum mechanics and why we need it and what's weird about it, because there are some pretty weird things in quantum mechanics. Now, as I look out on this august audience, I'm not sure that I'm maybe pitching this too low. So if I am, well, Felix Bloch once said there's nothing as enjoyable as listening to somebody talk about something you already know about. So I hope that's the case. In 1900, so as I said, we were talking about having 3 different lectures building up to things like entanglement and Bell's inequalities and some wonderful stuff. But I thought today what I wanted to do was start with the wave-particle duality, which poses the central problem of quantum mechanics. Richard Feynman famously said it's the only mystery. He later modified his views and said, no, it's not the only mystery in quantum mechanics. There are 2 mysteries in quantum mechanics, and entanglement is the second one. So what I'm going to talk about today, though, is wave-particle duality, the first of the 2 mysteries. And, you know, in 1900, everybody knew that electromagnetic radiation was a wave. A wave is something which distributes itself continuously in space. And everybody knew that electrons were particles. And probably a characteristic of particle that's most distinctive is that a particle is localized in space, and its property, it has inertial mass, you know, and it can have electric charge in the case of electrons. And it's interesting when I say that in 1900 everybody knew this. They only knew it for about 12 years. I mean, the electromagnetic radiation was only first produced in the 1880s by Heinrich Hertz, although it was predicted by Maxwell in the 1860s. And the electron was only discovered in 1897. So 1900, I say, everybody knew all this stuff, but they only knew it for 3 years. Now, 25 years later, everybody knew that electromagnetic radiation was made of particles, and everybody knew that electrons were waves. So what's going on in the 25 years that you go from this thing being a wave to being a particle, and this thing from being a particle to being a wave? And the answer, I give away the answer, this is like, you know, spoiling the movie, but the answer is that at the end of this process, people are seeing that both properties apply to both entities, light and electrons. Now, this is not an obvious thing to do, because I want to just review some sort of basics of waves and show you why there's almost an internal contradiction as you make these assertions. And so I'll tell you a little bit about what distinguishes particularly waves. And these are the properties of waves. I would like to emphasize that waves are continuously distributed in space. We have examples of waves, water waves, sound waves, and light. Now, you take light, the fact that light's a wave, most of you take on authority. Water waves, that's okay. I mean, you can go to the beach, or you can look at your cup of coffee. There they are, rippling across the surface. Sound waves, you know, Chaucer in the 14th century knew that that sound was some kind of wave phenomenon. He writes in some of his poetry that it's like the ripples spreading out from a rock in a pond. So I think that's pretty insightful for the 14th century. Light, though, as I said, was only understood to be a wave in the 19th century. In fact, Newton thought it was particles. And his authority kept people from realizing that it was a wave for a couple hundred years, not until Thomas Young at the beginning of the 19th century first exhibited interference. And interference becomes the defining property. If something exhibits interference, it must be a wave. But I need to talk to you a little bit about some of these properties. And so what I'm going to do is just show you some stuff which almost everybody in this room knows, and so too bad. But it also gives me a chance to show you a grapher, which if any of you have Macs, is one of the great hidden secrets of Mac computers, that it has in it a thing called grapher, which is a wonderful piece of, let's see if I can find it, if it's so wonderful. Yeah, there it is. So this is just to let me show you a few things about waves. And I have to get down on my knees, I guess, to do this. Most of you know that a good representation of a wave is just a cosine wave. And I've got this cosine wave here, and it goes up and down. And I've actually added a constant to it to bring it up to rest on the x-axis. And, you know, again, just for those of you who need to be reminded, the wavelength of the wave is the distance from crest to crest. The period of the wave is if the wave is traveling. And I can actually make this wave travel. Let me see if I say that. This is true. Actually, I guess what I can do is I can make that wave travel. And so,
just give you a chair in case that helps.
well, I need to get on my knees here. I think it's better. Yeah, so there. I can make it travel a little ways, and then it bobs back and travels some more. But of course, if you sit here then and watch the thing go by, the time that it takes from one crest to move to where the other crest is, that's the period of the wave. The reciprocal of the period is the frequency of the wave. You know. Why don't we hand these around and see until they run out? I obviously don't have enough, but it's an outline of some other things I'm going to talk about, not this. So you have these three properties of the wave: the period, the frequency, and the wavelength. And the wavelength and the frequency, or the wavelength and the period, is related to the velocity of the wave. This, what I really wanted to tell you about here is to get us a little bit on towards quantum mechanics, is again something I think most of you know, which is I can build out of these cosines any shaped wave I want. Does not have to be the cosine. Those of you who know about Fourier series know that this is the thing you can do. And let me show you what I mean. So I'm going to turn off my animation. I'll go back to this guy. So there's my cosine wave. Now, what I'm going to do is I'm going to add together some waves to make a different waveform. I'm going to make a square wave, which is kind of not an unusual thing to do. I'm going to take this little wave here, and I'm going to add it to the big one. And you can see what's going to happen when I add them. This piece here is going to subtract from the top. It's going to take that much off the top. This piece here will take this much off the corner. This piece here will actually boost this corner a little bit, and so on. Now, the fact that you can do that with waves is called superposition. Fancy physics word, meaning you can add them. All right? And it's nice that you can add them. And the fact that you can add them means you can go on and put together a combination of these things. Like here's another one, a smaller one. I can add it. And if I add those three together, you see, I get this guy. And you can see he's starting to be kind of squarish. And I'm allowed to add as many of these things as I want. So what I'm going to do is, I thought, being a prodigal sort of person, I thought I would add 100 of them together. And when I add 100 together, there you can see I've got a square wave with a little ripple. In fact, anybody here who's done signal processing knows about this little peak that shows up here. But my point is that the waves add together. Superposition, another very important feature. Turns out this is a very important feature in quantum mechanics. And it has some very odd properties that make it different from the fact that you can just add these waves together. In quantum mechanics, well, let me back up a second and say that in signal processing, again, those of you who have done any of this know that if you put a filter on this thing, you will find, you can extract from it those frequencies, the frequencies of those waves that I added together to get this shape. So you can actually pull them out on an oscilloscope if you want. What's interesting in quantum mechanics is that you can imagine you're making a measurement here to get the frequency out. And what quantum mechanics says is, well, I've got this thing, and I'm talking a little loosely, but not bad. I have this thing here which represents some quantum state. And the word state in quantum mechanics is quite vague. It just means what you've got. And, but you can represent that state by adding together a series of functions, not unlike the Fourier series functions. What quantum mechanics says it's interesting is that if you make a measurement, you will get one of those frequencies. You won't. And now if you make another measurement, same system set up the same way, you may get a different frequency. You'll get one of the composite frequencies. This is a little disturbing because we're used to experiments where if you set everything up exactly the same and make exactly the same kind of measurement, you should get exactly the same answer. No, not what quantum mechanics says, not what in fact happens when you set up an experiment with quantum mechanics. You would go in and you think you're going to measure, most of the time for this one, you would get the frequency of that big fat cosine wave. Somewhat smaller fraction of the time, though, you would get the frequency of the next higher frequency wave. A smaller fraction of the time yet, you'll get the other. But this is very much the essence of quantum mechanics. You make these measurements on the system. The state, the state is actually prepared by what you've done in a laboratory, let's say. And the measurement that you get will be one of several possible answers. And it will be that way as you go on. So that's kind of, I think, nice to see as we go through here. Another point which I'm not going to elaborate on is, which is interesting, is because if we're interested in wave-particle duality, is I can actually add together enough sines and cosines to make a very narrow pulse. And I can cause, this one you see is periodic, and you can see that the other waves, the other pulse, the other squares are there off the side, and they go on both infinitely to both directions. But I can, if I add together enough sines and cosines, and I do it in the proper way, I can actually make those space between these two things get bigger and bigger and bigger until the ones at the left and the right have gone on out to infinity, and I'm left with one sitting right in the middle, very sharp. Called a delta function, but I can do this. And that begins to look localized. It looks localized all by itself. And it's not very hard to put the time dependence in. Then lo and behold, you have this single pulse that's moving. So you see, there is a kind of possible connection between waves and particles. You can build out of waves something which looks very much like a particle. It's called Fourier Integral, but again, we don't have to know that. So let's go back to my slides. Oh, well, all right, I did leave out something, and you're going to wish I hadn't, but let's see. All right, so here is what we saw with an interlude with this nice piece of software that comes with every Mac of a certain age. Wave-like period frequency. The amplitude, that's pretty good. Superposition is pretty good. What I left out was the question of phase. And phase turns out to be important enough so that I have to at least wave my hands at the idea. And the idea is that if you have, say, a wave going along like this, you can have another wave that you're going to add to it. And you can see that it's possible that I might have a valley of the additive wave here and a peak of the additive wave there. And when I add them together, I'm going to get nothing. That's destructive interference. So destructive interference is just another term for superposition. They're all superposition. But the other thing, which is, you can see, if I then sort of shift my imaginary wave that I put here, it's my chance to use Larry's picture there, so why don't I do that? Well, I won't do it because it'll take me too much time. And, but as you can see that there, if you imagine two waves together, one is not quite overlapping with the other, then we would say those two waves have different phase. And the use of phase, we don't have to really know much more than that, but I mean, it's measured in angle. It's a fraction of the 2 pi radians in a circle. So we would have two things which are in phase, where they exactly lay over each other, and we have two things which are exactly out of phase, when the peaks of one lie under the valleys of the other. And then we have things which are in some other phase relationship, when the angle between them is a little different. So that's the idea of phase that we'll use here. And I see here this kind of nice comparison. I mean, the wave that most people always see a lot of is, of course, 60 hertz. The wave that's, if you stick an oscilloscope into the wall receptacle, you will see a beautiful cosine wave, and it will have a period of 1/60th of a second. It'll have a frequency of 60 cycles per second, because they're working very hard in the utilities to produce a wave of exactly that frequency. Just for comparison's sake, electromagnetic radiation in the visible spectrum has frequencies of 480 trillion hertz, not 60 hertz, a little more. And so the period is going to be fractions of a trillionth of a second. The T, well, never mind the T. T is trillion, it works fine. And so you have this correspondence that, again, red is wavelengths of about 600 nanometers, blue is 400 nanometers, and that's the visible spectrum, and it has a frequency span from about 500 terahertz to 750 terahertz. Tera is what physicists use for trillions. So that's what you need to know. Interference is another name for superposition. Constructive interference, destructive interference. These are unique properties of waves. I think any physicist asked would say, if it exhibits interference, it is a wave. And that's how Thomas Young proved to the world that Newton was not right in saying that light was made of particles. Because in about 1800, he did an experiment that showed interference. And I was going to do this with YouTube, but every time I've tried to do it with YouTube, it doesn't work. So I'll show you the diagram instead. And this is known in the trade as the double-slit interference experiment. And this is basically what Thomas Young did in about a little after 1800. He had a wave coming in, so that's supposed to be a crest, let's say, and that's another crest. Actually, he was using ordinary light, and so he had over here, he had a pinhole quite a ways back, so that the light came through in crests that were circular, but as they got farther away, they got flatter, and so it looks like a straight line pretty much. And then he put it through two slits, two holes. And the waves overlap, and when they overlap, you get a pattern like this. This is actually done modern. He was using sunlight, which is tricky to do, and it's faint, it's hard to see. Today we use lasers. The laser is very bright and has a very nice property that I'll mention later. But you can see the pattern here. It's an interesting pattern because you can see there are these little bright lines with the dark lines in between them. In the trade, they're called fringes, because they are kind of fuzzy on the edges. But you can also see that there's a pattern here which is bright, dark, bright, dark, bright. That's interesting because that is a pattern you'll get from a single slit. But you won't get the little dark lines in between. You have to have two slits. So the double-slit interference is what produces the very fine structure here. And the single slit would produce a kind of muzzy, no lines in it, muzzy, no lines in it, bright, bright. That's a single slit diffraction pattern. And when you put two slits together, it turns out their single slit diffraction patterns lay right on top of each other, and the interference pattern lays out these little fringes. It's very nice. We can do that. I'll pass this around. It's modestly amusing. Let's see. Oh, yeah. I never travel without a laser these days. You never know. You're going to have to stop and talk to somebody about it. It's useful to have glasses. So it turns out, interestingly, that two slits is the experiment we talk about all the time. But let's see here. Yeah, two slits is what we talk about. But if you have a lot of slits, the effects are even more dramatic. Let's see. Can you see this? No, you can't. I was afraid of that, but let me see. What I'll do is I'll hand it around. Yeah, now you can see. Let's see if I'm not in the way. Notice that instead of one dot, but if you use multiple slits, there's more dots. And this is about 5,000, what it says on it. Well, this is 1,000 lines per millimeter. Not two slits, 1,000 slits. 1,000 slits in a millimeter. It's a diffraction grating. It's a fundamental tool for examining the properties of light. And it has this, oops, that's the wrong one. Let's see, this one. And it has this property, you see. And I'll just hand this around. You can actually do this on the table, top. See for yourself, I'm not lying.
Don't try it in your eyes.
Yeah, these are not that bad. I mean, you won't be blind for very long. But
One eye at a time.
and I'll show you just so we aren't favoring one side of the room over the other. Oh, well, if I get this open, yeah, there we go. Here's another. And same thing. Same thing. Oh, yeah, it's a little faint, but just to keep things interesting, I'll give you this one. Now you can play it on a piece of paper, pass it around the table, and you'll see, same thing. Oh, no, that's not how to do it. Shine the light through it. Now, the button is up front, right there. Okay, but don't point it at me. All right, so these are interference effects. It's interesting that when you have many, many slits, and the light goes through many, many slits, a single wavelength, a pure wavelength, such as you get from a laser, actually will add up and collect so that they all go through in one spot. It's a very well understood effect, and it's very wave-like. You could not explain this until you had the wave theory of light. All right, now, so that's the story on interference. That's what I wanted to tell you about. Now, what I want to tell you about is how did our patent clerk and our prince get us to the point where we had to have quantum mechanics? So the patent clerk, of course, is Albert Einstein, technical expert, third class in the Bern Patent Office, when in 1905 he published Special Relativity, Brownian Motion, Photoelectric Effect, and a bunch of other stuff. He clearly didn't have enough to do in that office, you know. Actually, he was notably quick and able in what he could do in the office, and so then he had time at the end of the day. I have have a daughter who's a patent examiner, but I've been waiting. Anyway, so here's one of the, this will get us prep for what Einstein did in 1905 that made us have to have quantum mechanics. There was something called the Photoelectric Effect, and it had been known since the 1880s. As soon as Hertz was able to produce electromagnetic radiation in the laboratory, and he did this by oscillator spark gap, and he'd have a spark gap that was driven on one side of the laboratory, and then across the other side of the laboratory he'd have another spark gap with a resonant oscillator, and so he would make sparks here, and then sparks would occur across the room. And so he knew he had produced something that had traveled across the room. 30, 40 years later, we're doing transatlantic broadcasts with this stuff. It's really pretty amazing. Anyway, but somebody else noticed very early on that if you shine UV light on the electrodes on the other side of the room, they would spark much more easily. Something was going on. And this was called the photoelectric effect. That if you shine light on something which has electrons in it, everything, but in this case metal, and better if it was an alkali metal, you wanted something where the electrons were easy to get out, as you found, then electrons came out. So this is okay. Now, how does this occur? Nothing wrong with this in electromagnetic radiation. You have this picture that the wave comes in, the wave brings energy into the metal collects enough energy, and there's finally enough energy so that it maybe evaporates an electron out or something like that. No, that is not how it happens, and this is what was disturbing to people. What you found out was, first of all, there's a cutoff. If you have light of too low a wavelength, too long a wavelength, too low a frequency, then nothing comes out. And it doesn't make any difference how much you crank up that light. I mean, at some point, I suppose you melt the metal, but that's not what we're talking about here. Just no electrons come out. So instead of that, what you find is that if you change the frequency of the light, if you shorten the wavelength, raise the frequency, then suddenly there's a threshold. And at some point, electrons will come out. You look at the energies of the electrons, and as you would expect, they got a lot of different energies because they're coming out of the surface of the metal. There's a bunch of stuff that can happen to an electron. But there is a maximum energy. And no matter how much of the light you pour in at your higher frequency, yes, electrons are coming off, but they don't come off with more energy if you jack up the intensity. Doesn't happen. So what's going on? Another thing which is kind of interesting, and people also had discovered, was suppose you cut down the intensity of the beam. Kind of first thought is, well, if I make the beam really weak, it'll take a while to accumulate enough energy to push the electron out. No. The electron either comes out immediately on being irradiated or it doesn't come out. So this phenomenon was one that Einstein knew about. But for reasons that had nothing to do with that, he concluded that, contrary to what everybody was thinking of at that time, he concluded that according to the assumption considered here, the propagation of a light ray emitted from a point source, in that propagation, the energy is not distributed continuously over ever-increasing volumes of space. He's saying, but consists of a finite number of energy quanta. Doing this in German, he's actually coining Lichtquanta. Lichtquant. Localized at points of space that move without dividing and can be absorbed or generated only as complete units. And he says the energy of one of those units would be proportional to the frequency. Max Planck had just a few years earlier suggested that thermal radiation could be understood if the surfaces of a container in which you had radiation only absorbed or emitted light in chunks proportional to the frequency. That's why the constant is Planck's constant. He got it first, but he did not believe that the radiation was continuous. Einstein is making an extremely radical proposal when he says, no, it isn't that it absorbs and emits in quanta, it's that the stuff is quantized, that the energy is being delivered in packets. And a packet has an energy equal to HF. And you think, okay, I can take that. It's a simple equation, it's only got 3 letters in it, that's my kind of equation. But think about that. The frequency is a property of something which is continuously distributed in space. The frequency we introduce to explain what's going on with a wave. And here suddenly we're taking this concept of frequency and we're making it say something granular about particles. This is you're twisting your head when you do that. This is not a happy moment. It's not a happy moment for all the physicists of the day. And in fact, almost nobody believed what Einstein said. And a very famous American physicist decided that he would prove Einstein is wrong. He would actually do the experiment. And so this is Robert Andrews Millikan. And he says in his paper that he writes in the Physical Review in 1916, Einstein's hypothesis may well be called reckless. First, because an electromagnetic disturbance which remains localized in space seems a violation of the very conception of an electromagnetic disturbance. And second, because it flies in the face of the thoroughly established facts of interference. He says that in a paper in which he proves quite conclusively that Einstein is right. So he's proving that Einstein is right, and he admits that he's done that, but he says, I still don't believe him. And that's very Millikan-ish. I remember my major professor in graduate school said to us at one day, he said, you know, we used to say that the unit of self-conceit is the can, but it's too large a unit, and so we use the Millikan. But he was a very clever man. He was also head of Caltech for many years. So many of those of you who associated with Caltech will know. Here's his experiment, which is very lovely, and I just thought I'd show you the apparatus because it is quite lovely. This is a difficult experiment to do. He's going to try and find out, measure the maximum energy of electrons that come off. And he's going to try and show you that maximum, actually he was trying to show you that it wasn't true, but he ended up showing it was true, that the maximum energy that comes off is equal to the energy of this chunk. Here's HF, minus a constant, because the electron is actually bound inside the metal, and so you're going to put in a chunk of energy. You're putting in an HF. It wasn't until 1926 that we coined the word photon. So here he is in 1916. He didn't call it a photon in those days, but we can call it a photon. So you're putting in a single photon with an energy HF. And the energy, the maximum energy the electron can get is the energy that you put in minus what it takes to break the electron off. There are lots of ways for the electron to lose more energy. And so if you look at the electrons, there will be a lot of different energies. But he was measuring the maximum energy. And this is a hard experiment to do because you all know, if you've done anything with surfaces, you know that surfaces are mucky and they resist. You can have a very clean surface in a vacuum, and within seconds it will have oxidized. It will have picked up garbage out of your not so great vacuum, the vacuum that is not as great as you thought it was. So what he did, which is kind of clever, is first of all, it's all going to be done in a vacuum. So this is a tube. This is a glass tube. And he has here 3 samples, and he has here a rotating knife so that he can bring a sample down and he can scrape a layer off the surface so the surface is clean, then rotate it around to here, send in his light, And then he can measure his electrons as they come out and are drawn to this positively charged electrode here. And he can see how many electrons come off. And he can, by adjusting the voltage, measure their energy. So it's a very, very nice experiment. And he can do all this fairly quickly, as he must, because in a short time, his vacuum, not being any wonderful vacuum back in those days, I don't know, could he get 10 to the minus 6 torr? He might. The surface will absorb and begin to lie to you about how much energy it takes to get an electron off. It will give you a different answer. And then he just cleans another surface and puts it there, and cleans another surface and puts it there. So it's very clever. And then he plots the maximum energy along here. It's in volts. We don't have to worry about that. And he puts his data points there, and he gets a straight line which has an intercept, which is this number called the work function. We don't care about that. So it's an absolutely beautiful verification of Einstein's prediction. And you can now understand some of those properties, why a photon coming in to the photoelectric effect, why it acts instantly or not at all. It's because all the energy is there to break one electron loose, and it either happens or it doesn't happen. There's no build-up. You know, classical electromagnetism would say there should be a build-up. There isn't any. And so that brings you to this situation of saying, oh my God, this stuff which I always thought was a wave is particles. Again, nobody was eager to believe Einstein, even with Millikan's data. I mean, you saw that Millikan didn't believe it. However, a few years later, the American physicist, Arthur Holly Compton, he's a brother of the Compton who was president at MIT for many years, was doing an experiment with X-rays in which he was putting X-rays into a gas and observing that some of the X-rays, if you looked at an angle, some of those X-rays came off at an angle. That was interesting in itself because you're putting the X-rays that way, and yet here comes some this way. They come off with a reduced frequency, with a reduced energy. And he explained it beautifully by saying, you know, this is just a billiard ball collision. A photon has come in to the gas and has bounced off an electron. And if you, this was not a difficult physics problem. I'm not showing you the data, but anyway, that turns out that if you look at the change in frequency as a function of angle that the photon comes out, it's undergone a hard sphere collision with an electron. Very chunky to do that, you know, that's a photon. That's not, there's nothing distributed in space about that baby. And pow, and off at the angle. And so that did it. And 1921, Nobel Prize went to Einstein. And it was not for relativity. It was for the photoelectric effect. And there were still people who weren't sure about relativity. But, and he, I won't go into the history, he didn't get it until 1922. Anyway, that's kind of the story of photons. Now you have wave-particle duality for light. The flip story is from our prince. This is Prince Louis Victor Pierre Raymond de Broglie. And he was of the de Broglie family. The eldest member of the family is the Duke de Broglie. And all the junior members of the family are princes. So he's a junior member. And in fact, that's how he happened to become a physicist. It was not normal for French princes to go into physics. But his elder brother did go into physics. His elder brother, the Duke, was a physicist. And that very much influenced Louis. He started to do physics, but he had to take off 4 years because of World War I. And then he came back from World War I and took up physics again. And he looked at what Einstein had done, Einstein's theory of relativity. And looking at that theory, he said, you know, if energy and mass and momentum are related in the way Einstein says, isn't it possible that frequency and wavelength are related in a similar way? And so, without explaining any of this, to me either, he was able to infer from the structure of Einstein's relativity theory that it was plausible that particles should have a wave-like property. And that if they did, they would have a wavelength which would be equal to our beloved h, here it is again, showing up, divided by the momentum of the particle. Sometimes you write that as mv. I'm writing it as p because it turns out that equation works for photons as well as for electrons. And then so he does that in 1924, and 5 years later he gets a Nobel Prize for it. He wouldn't have gotten a Nobel Prize for it except for a couple of Americans and a Brit. But Davison and Germer, working for General Electric, were doing an experiment around that time, and they got something that happened that was very strange. And I don't know, Davison found out about his idea and realized that what they were seeing was that electrons were diffracting in a crystal just the way X-rays diffract in a crystal. And that they were diffracting in a crystal as though they had a wavelength of this. You took the momentum of those electrons and you looked, and lo and behold, they were diffracting. Well, diffraction is an interference phenomenon. And he concludes, this is a little extensive, but the electron can no longer be conceived as a single small granule of electricity. It must be associated with a wave, and this wave is no myth. Its wavelength can be measured, and its interference is predicted. And this was all true, established by 1929 when he got his Nobel Prize. So, here's a picture. Let me tell you about this, if I can make it work. All right, it will work in a moment. So, we can today do the following experiment. There's a famous Japanese physicist named Akira Tomonura who advanced the whole field of electron optics. I mean, you know, there's an electron microscope. There's an electron microscope because electrons will behave like waves. But what's really interesting is the following question. If these things are particles, and they're going through your interferometer one chunk at a time, how do they interfere? I mean, what are they interfering with? This is really the basic mystery that Feynman talks about. Can you put, I mean, we can ask about photons. Suppose I put one photon today, and I put another photon tomorrow through a double-slit interferometer. Do they interfere with each other? Well, the answer, turns out, has to be that it interferes with itself. Because you put them through one at a time, you will get an interference pattern. So that's what I'm going to try and show you here. Now I made it go away. And so what we have here is an experiment, or the results of an experiment, that has now been done several times. You watch on the screen. These are electrons coming through a double slit arrangement for electrons. And you can see here, I get these spots. The electron is arriving at my detector. It's a chunk. It's making a single spot. It's localized. They're coming more and more. At first, they're showing you this at about the rate they actually did the experiment. And then because they haven't got time and we haven't got time, they speed it up. All right, they go much faster. And then as we get towards the end, they slow down a little bit. But you should begin to see fringes appearing, kind of like a bright band, dark, bright, not so bright, not so bright, 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 bright. And this is happening one at a time, 1 per second is coming through roughly. And so these electrons are producing an interference pattern. Therefore, they are waves. And you're doing it one at a time. And there is why you need quantum mechanics. And you'll see in a minute, or no, maybe not this time. Yeah, I'll try and show you. You'll see in a minute why it's so unsatisfactory, even though you need it. But there, nice interference pattern, all built up. And I think I just, so that you could all appreciate that, I show you a succession from Tamanura's work. Those are a sequence of time photos of the electrons arriving. Same point. You end up with fringes, even though the electrons have come in slowly one at a time. Little digression. Just, I think it's interesting to see some of the implications of this de Broglie wavelength thing, that it's h over the momentum. And when I teach, I will always use electron volts as the energy units. You don't really have to know what an electron volt is. It's a pretty small energy unit. But what I want to show you here is the relationship, the relative sizes of these things. So here's I think, an important idea to keep in mind. If you want to look at something small, you need a probe which is comparable in size to the thing you look at. You know, it's like if you want to pick up things with your fingers, you can only do things that are not much smaller than your fingertips. Same thing with light. If you want to look at a small object with light, you need a wavelength that's at least as small as the thing, or of the order as small as the thing you're looking at. So, for example, I handed those lasers and diffraction gratings around. Those diffraction gratings had lines that are roughly 1/1,000,000th of a meter apart, 1 micron, 1 or 2 microns, depending which grating you had. And so if I want to look at something and see the effects of 1/1,000,000th of a meter, 10 to the minus 6 meters, I am going to need something which has a momentum corresponding to an energy of I read down here, 1.2 electron volts. That's optical. Optical photons have energies that run from about 2 to 4 electron volts. That's stuff that I wrote down with the trillions of hertz. Trillions of hertz is about an electron volt, 2, 3 electron volts. But now if I want to look at something which is 10 to the minus 10 meters, so that lambda is going to be a factor of 100,000 smaller, then I'm going to need something which is 100,000 times more energetic. I'm going to need 12.4 keV. 12.4 keV is X-rays. That's what you're getting when you're using X-rays. So if you want to study the structure of matter, use 12.4 keV X-rays. If you want to study it with electrons, same thing. If you want to go inside the atom and look at the nucleus, the structure of neutrons and protons that we think sits at the heart of every atom, well, that's getting down. That's about 10 to the minus 14 meters. And you're going to need something of the order of hundreds of MeV, millions of electron volts. So when you start talking about how you're going to do this, you build accelerators. And you'll ask somebody, how big is your accelerator? And they'll say, it's 124 MeV. Or it's 100 MeV. I did graduate work with accelerators that were 10 MeV, 20 MeV. If you want to look at the proton, the individual proton itself, and you want to see structure down inside the proton, then you're going to have to go down maybe to the thousandth of the size of a proton. And that'll take you to TeV. And if you watch what's going on at Fermilab in Illinois or at CERN in Switzerland, they're building things that will take you up to 10 TeV. And now you're building an object that occupies square miles. You know, in the case of CERN, it runs under the border between two countries. It's big enough so that you can do that. This one is the one at Fermilab, the Tevatron, cleverly named, at Fermilab, is big enough so they can graze bison in the middle of the field that's above the tunnel that contains the accelerator. Well, I'm going to stop there. I'm not going to tell you about the Planck length, which is thought to be the ultimate length that there can be. Instead, what I want to do is, coming to close to the end, I want to show you a different kind of two-slit interferometer. This is called a Mach-Zehnder interferometer. It's beloved of optical physicists these days. And it's rather simple. You would have a source out here, might be a laser. And you have here a beam splitter. So you can build a device. Well, I mean, actually, if you just take an ordinary microscope slide and shine a beam on it, most of the beam will go through it, but 4% will reflect. So you're splitting your beam into 4 and 96%. But here, you can actually build them so they split 50-50. So the laser beam will come in, and it'll split. Half of it will go this way, half of it will go that way. You put mirrors here and here, and so this one goes up and comes this way, and this one comes over here and goes this way. Now here's another beam splitter. So this guy's coming in here, half of him will go this way, and half of him will go through. This guy's coming up here, half of him will reflect and go through this way, and half of him will go through that way. So the two beams are being recomposed up here at C and at B. So one lays on top of the other there. Now you can move the mirror. And if you move the mirror, the path length here will be different from the path length there. And the phase between the two waves will shift a little bit. And so you can shift it from constructive interference to destructive interference to constructive to destructive and so on. So you can put a counter here. This is a little different now. We're not seeing things with our eyes. You put a counter here. And as we move this, we would see the pattern change. And so here's what one might see with detectors up here and here. As I move this mirror, I will see a lot of counts for one mirror position, say 0, and then I will move it to no counts, and I will do sort of 5, it says I'm doing 5 seconds to take each of these data points. So I move the mirror, take data for 5 seconds, move the mirror, take data for 5 seconds. There is an interference pattern, for sure. And it is called fringes in the business. I mean, it's a long time since anybody's seen an actual fringe. But this is what these are called. This pattern is known as a fringe pattern. Anybody's seen it. So it's quite beautiful. But it's even more beautiful for the following reason. You can have a device here called a parametric down conversion source. It has the following property. If I put a laser beam in with, say, a short wavelength, it will split the wavelength into 2 longer wavelengths. It conserves energy, so the sum of the energies of the photons going out will equal the energy of the single photon coming in. But it happens instantly. And for reasons that I don't really know, one photon is called the idler, and the other photon is called the signal. And what's nice about it, though, is that you can now do coincidences between, say, here and here. That will tell you that, for sure, only one photon has come into your system. Because you're only going to record with these detectors if you know that a photon was launched this way because you saw the idler photon there. That's a way of assuring you've got only one photon in your system. And the interesting thing is, if you don't know, if there's no way to tell which path this photon took, you will build up this pattern, one photon at a time. It's just the same thing that you see in the Tamanura data. You're getting an interference pattern. That photon, did it actually go along both paths at once? Well, if you know the other part of the story, I remind you, anything you do to find out which path that photon went destroys the interference pattern. You can put a Polaroid filter here and a Polaroid filter there, You can arrange them so that if it came this path, it was right polarized, or this way it was left circularly polarized, or linearly polarized this way and vertically polarized. As soon as you do that, the interference pattern disappears. As soon as you can tell what the path is that it took, the interference pattern is gone. I'll show you one more example of this, and I'm done for today. This looks complicated. That's why I put it on the outline. But it's kind of the same thing that I just told you about. This is an experiment that they did at University of Rochester. And so here's your laser. You come in here. You split the laser beam into two and send them along these two paths. But here you have a crystal which divides it. It's the same kind of thing we had before. It divides it into a signal photon and an idler photon. And this one comes through this nonlinear device which splits it into a signal photon and an idler photon. So, very nice. Signal photon comes here, and it's combined by this device. It's another beam splitter, so that two signal photons are arriving at this detector. Now, I can put another detector down here and look at the idler photons. Well, this may be a bad place to go, but anyway, so think about this. I can have two photons arriving here, and I can move this mirror up and down. That'll change the path. That'll produce this same kind of interference fringe as I showed you in the previous slide. But now, I can look and see if the idler photon came from here. On the other hand, so how can I do that? Well, I'll put a filter right here, neutral density filter. I'll just block the I1. So now I can tell whether a photon that arrived here, if a photon arrives here and I get a coincidence between what's here and what's here, I know that photon must have come along path 2. If I don't get a coincidence, then I know it came across path 1. What happens to the interference pattern? Disappears. There is no interference pattern. If I take this filter out, so that, and I get everything, this is tricky alignment, but I get everything perfectly aligned so that I1 comes down through here along exactly the same path as I2. Now I can no longer tell which path. A coincidence doesn't tell me whether it was a coincidence between an S2 photon and an I2 photon, or between an S2 photon and an I1 photon, or I1 and so on. I cannot tell. What happens? The interference pattern comes back. This drives people nuts. Okay? There is a spectrum of experiments, and it'd be kind of fun, and maybe I'll show you a couple if I go on to do the next two pieces that I promised to do. If I do that, I'll show you some of the brilliant attempts to get around this, and how every time they fail. As soon as you can distinguish, even in principle, I mean, you look at this thing and you say, oh yeah, I see, I don't have to set it up. I mean, I don't actually have to read the counters. I don't have to do anything. I just have to look at it and say, oh, look, there's no way this apparatus can tell one path from the other. Interference. Soon as I put something in there so that it's possible, in principle, to discern which path it took, it's gone. Distinguishability is the crucial feature. What happened there? I thought I had one more slide, and I don't. So that's a good place to stop. Wave-particle duality drives people nuts, and you need quantum mechanics to get the results to come out right. Quantum mechanics doesn't leave you feeling very satisfied, but it does describe with amazing precision a whole spectrum of phenomena that creep us out when we think about it. Einstein famously said, this theory has in it spooky action at a distance. Spukhafte. Spooky action at a distance. Erwin Schrödinger, who in fact devised the wave theory of quantum mechanics, said of these phenomena, I don't like it, and I wish I had never invented it. So that's a good place to stop. You can go home thinking about that. And I'll stop there. Questions, of course. Thank you. Yes.
You made it sound like it was easy to make a single electron or a single photon. How do you build a device that emits a single photon or a single electron?
Well, you know, in a way, a single electron is kind of easier than a single photon because you just turn down the beam. I mean, you know, or you put filters that take out some. You keep making it weaker and weaker until you're pretty sure there's only one there.
Okay.
That does not work so well for photons, as it turns out. And we needed some refinements of the theory. So the way it was actually done in some of the early one-photon experiments was to arrange to excite an atom to an excited state. Well, when an atom decays from its excited state to a lower state, out comes one photon.
Right.
So if you were pretty sure that's how you were making your photons, you knew you were producing one at a time. That was the early one. Another way is the way I was showing you here, where you use these down converters that take an incoming photon and split it into two photons, and then you use one photon really as a tag to tell you that the other is there, and it's single. But yeah, these experiments, well, I mean, that's more history, but they can be done. Yes?
This might be obvious, but maybe rather than having a particle and a wave at the same time, suppose at each wavelength you pop up with a particle, and then it goes back into a wave, and then a wavelength further down, a particle pops up, and then goes back into a wave. And so it's discrete steps that shows up.
You know, there's a whole set of theories that there's something called the pilot wave. Maybe particles, and maybe it's pretty much what you're saying. It's not a bad idea.
Discrete.
Yeah. That is, that somehow or other they're both present, and for example, the one particle is guided, knows about the two slits because there is this accompanying wave that is in some way talking to the particle. But nobody's been able to figure out how to describe that mathematically or make a theory out of that. They're still trying, because there's a whole sequence of people. Feynman famously basically said, I don't care. If this is the way it is, this is the way it is. Stop fussing about it. Other people say, I can't stand this. I mean, Einstein was one of the, I can't stand this school. So you're in good company when you suggest that. But nobody's been able to make it work. Next time, I'm going to try and show you why, at least in one whole entire class of theories, it can't be made to work. I mean, there's a whole class of theories which said, well, maybe somehow or other buried inside the photon there's information. It knows about the two slits, even though it's only going to go through one.
Well, you can't prove that it's electron at discrete points, and you can't actually prove that, I guess.
No. And, you know, you can see a problem. Famously, it's kind of built right into the structure. I didn't go into this, but if you have two slits, and you say, okay, the particle's coming through here, I want to look and see which slit it comes through. Well, okay, I'm going to have light that bounces off the two slits and interacts with the photon that's coming through in order to see it. Well, you might be able to do something like that. Now, what happens, though, of course, is that, well, classically, we have to have a short enough wavelength to be able to tell the difference between the distance between the two slits. Well, what happens if you have a short enough wavelength? You now have a packet of energy. And that packet of energy interacts with the electron or the photon that's coming through there. And it blitzes it. You know, you've lost your interference pattern as soon as you've done that. I mean, classically, we would have said, no, there's no problem. You just make that short wavelength ever weaker. You keep turning it down and down and down until it's still able to see the distance between the two slits, but it's still weak enough so it doesn't bang the photon out of the way.
Can you go to a low enough frequency where the wavelength is far enough so you can?
No, that's what happens. You can go to a lower frequency, but the wavelength gets longer, and pretty soon you can't see the difference between the slits. And then when you get there, the interference pattern is back. Actually, that experiment has been done. People have sort of cranked it steadily, and you can see the interference pattern slowly fade away as you get closer and closer to being able to tell which slit the thing went through. Yeah.
There are at least 3 interpretations of quantum mechanics.
Yeah, that's true.
So the first one was the Copenhagen from Niels Bohr, and that's adhered to by, I think, 60-some% of physicists. And it's the one that says that psi squared or psi squared psi star gives the probability of detecting.
All the theories say that.
Right. So the second one's a multi-universe, which I don't understand at all.
Right.
And the third is a transactional interpretation of quantum mechanics, which purports to explain most of these phenomena about why when you detect one path, even when you detect, if you change the path even after, say, the electron has gone by, you destroy the interference pattern. It gives the explanation, makes a lot of sense, but you have to buy a couple of assumptions. One is that the psi wave is real, that the psi star mean a wave going forward in time and a wave going backward in time, that you have a transaction that is from, I'm sorry, it gets a little too complex for me.
Probably not good to put into a question.
The transactional interpretation came out in the 80s. I don't know if it has any following.
Yeah, I mean, these theories are around. There are three. There are more than 3.
Yeah.
So, some of them just seem kind of weird, and the adherence to the Copenhagen interpretation has a lot to do with Niels Bohr's kind of authority as a father figure to a generation of theoretical physicists, and he was famously comfortable with the weirdnesses of quantum mechanics, and he and Einstein had a famous set of debates. The sort of thought at the time was Bohr won every one of those debates. But if you go back and look at them, it seems that in many cases he just did not understand what Einstein was trying to raise as a question. And all that stuff has come alive again in the last 30 years or so. But I can't help you there. I'm an experimental physicist. I know the theory. As I say, some of the theories just seem to me like poetry. Somebody's saying something hopeful to make the discomfort go away. If you can't put it into an apparatus and verify it, I'm not happy.
What I've read is that working physicists say quantum mechanics works, and they ignore the various interpretations.
The aphorism is, shut up and calculate. Any other questions? I feel like I've taken way too much of Bob Primack's time. Sorry,
I
Bob.
think we may have to put mine off.
Likewise.
All right, sorry. That's my 30-minute
Because
clock.
I can come back anytime.
Okay.
So the poem could be photons are red, Electrons that are blue, quarks are neat things, and I love you.
Well, I hope that's a personal sentiment, yeah.
And let's remember that all of this is uncertain according to Heisenberg.
Wow. That's right. The Heisenberg uncertainty joke is very widespread, because I remember working with a guy named Bob Haxby from the University of Iowa, who said that Heisenberg had come and sat in his very living room at the University of Iowa, but they no longer could remember which chair he had sat in.
I have a question. So, imagine a photon leaving a distant galaxy from a blue star, and it travels across half of the known universe. And because the universe is stretching, it stretches the wavelength of the photon and becomes red. Where went the energy? Because red doesn't have as much. A red photon doesn't have as much energy as a blue photon.
You're saying it doesn't take energy to stretch the universe?
Does it give it up to stretching?
You're asking me a question I have no capacity to answer. I can speculate wildly, but it would seem to me if you're stretching the universe, you're probably doing something to the energy density. Well, you certainly are doing something to the energy density of the universe. You're decreasing it, and okay, so the energy has not been lost. You know, there are times when people are willing to give up conservation of energy. It's never happened yet. But if you imagine a certain amount of energy, let's imagine a ball of blue photons, and I expand the ball and make them red photons. Total energy in the volume is the same. Because you made the volume bigger, the energy per unit volume has gone down, but the total volume times the energy per unit volume is.
Well, I can see that, but what about a single photon?
Well, I would say it's the same thing. I mean, there's a lot of other photons out there too. There's the black body, the cosmic microwave. I would say that single photon is participating in that. That's the best I can do.
Well, thank you very much.
All right.